right, so let's talk about the photoelectric effect, which is what Einstein actually got his Nobel Prize for, and not the special relativity, as you probably thought. And what he noted was that light does not act as a continuous thing, which is weird for us to think. So imagine you sit in a room and you turn off the light and turn on the light, turn off the light, turn on the light, turn off the light, turn on the light. You obviously see what you can observe with your eyes, this sort of choppiness, right? That's inherent there. I have a light on, light off, light on, light. So I could see when the light is on, I can see when the light is off. My eyes detect that. What he noticed was that this detection is because we perceive that to be continuous. It's not really continuous. And I want you to think of a film. So I'm going to go here to YouTube and show you this this video of this car here. And this is done with 4 different sources. The bottom right is 1 frame per second. And the bottom left is 7 frames per second. And then it increases top right and then top left. You could see that when it's 1 frame per second, 1 picture per second, it's very choppy. You can tell that someone just kind of strung along a whole bunch of pictures to get you the video. It doesn't look very natural to you, right? The bottom left, you can still kind of see that, the choppiness. It gets a little better. Then 15 frames per second is much, much better. It looks much more smooth. And 30 is, forget it. That looks like exactly how it should look like, right? What I'm trying to tell you is that even the top left is just someone stringing along 30 pictures per second. All right? It's not the video is an illusion. All video is just someone stringing along a whole bunch of still images that we perceive as though they were continuous. What Einstein noted then is that light acts the same way, okay? Light, if you go down to a certain level, which we'll go down in a second, you will start seeing light like this. Light, just light. You could see light as flickering on and off and on and off, depending on how small you go, okay? And that is basically the crux of the photoelectric effect, okay? So when energy is given to a surface, here's a note that before Einstein even, when energy is given to a surface, light will come out. So think of that when you're doing metal casting. If I heat up a metal, as in I give it a whole lot of energy, it will turn red, right? Or orange or yellow or something like that, okay? That light is an indication that there is some sort of energy given to the surface. Okay, all right. What they noted, though, and what Einstein then strung along, is that if I don't give the material a lot of energy, I won't get the light that I'm accustomed to. So this particular example, I need to give it a lot of energy to see this with a visible eye, with a naked eye. But when we're talking on a smaller scale, you can start seeing these things even at ordinary temperatures. So what they notice is that small amounts of energy do not produce this light, okay? So basically now, what Einstein contributed to the table, what he brought to the table is that light will act like particles, not like a wave, meaning that it will emit these things called photons, okay? He kind of like honed in on the idea of a photon. And photons is what our eyes will perceive as an image, as light or something like that, okay? So if I don't give a metal or any sort of material enough energy, it won't release these photons. So I won't be able to see as many things coming out of it, okay? So instead of frames per second, think of it as photons per energy, all right? The energy unit, the smallest energy unit that you can give a material that will produce a photon is known as a quantum, which comes from Latin for packet. Okay, so meaning that materials take in packets of energy. If you give it half a quantum, it will say that not enough. I'm not going to produce anything. I can't. There's nothing. I can't. That didn't hit the threshold. I don't have it. Okay. You didn't give me enough. You didn't give me 2 quarters. You give me 1 quarter. I can't. The machine won't work. You need to give it exactly that amount or multiples of it. So if I give it 1 quantum, it will release, say, 1 photon. If I give it 2 quanta, it will release 2 photons. I can't get 1.5 photons. I can't get 1.25 photons. I have to do these in these packets, meaning that when I give it small, tiny amounts of energy, when I get to that quantum level, which is very, very tiny, it basically starts looking like that picture, that video from the bottom right, where it's very choppy. I'm going to be able to give it these packets and get these pictures coming out as 1 photon, 2 photons, 3 photons. When I give it a ton of energy, which is what we're accustomed to in our everyday life, everything looks continuous. It looks like the 30 frames per second, or in our case, probably billions and billions and billions frames per second. So quantum mechanics does not apply to everyday situations, but it definitely helps with the design of amazing devices and great ideas. It brought about lots of great ideas in scientific innovation in both chemistry and physics, and definitely in engineering. All right, so as basically as what I'm saying, that these small frame rates, the light does not behave like a wave, but like a particle, and we call a particle a photon. All right. The energy that's associated with one quantum is given as this. E is equal to Planck's constant, which is this constant, 6.626 joules times second. It's just a constant. 6 times 10 to the minus 34th. I'm sorry about this. 6.626 times 10. This is very important. I'm going to stop this because it's really irritating me. That so this is times 10 to the minus 34th joules per second. So I made a mistake. I'm correcting it real time just because it's such an important number. This is actually the smallest constant that we have in physics and chemistry and in engineering. The smallest named in value is 6.626 times 10 to the minus 34th. Think about how tiny that is. If you were to write this out, 0.000000006, it's a lot of zeros before you get to the 6626. And so E is equal to this number times the frequency of light. Okay, let's what we'll do is you know what, before we get to the Beer-Lambert's law, let's look at an example of how to use this wave energy to get stuff. So here I have the red line spectrum of lithium. I can see lithium producing light at 671 nanometers. Okay, I want to know how much energy that light is in joules. Okay, that's pretty straightforward, I think. Basically, if you give energy to lithium and you observe this under the under microscope or just, well, not just microscope, there's a lot of different ways of doing that, you will notice that at 671 nanometers you will see some light. So you want to know how much energy this is being emitted by lithium. So we will use E is equal to Planck's constant times nu. Fairly simple. And we know that for light, this is true, right? Because we discussed this, that wavelength times the frequency is equal to the speed of light. And I am giving you the wavelength. I'm not giving you the frequency. You can see here. So I need the wavelength. So basically, this is going to be equal to hc divided by the wavelength. That's also equal to E. They're equivalent. That's what that would mean. I could put this here, and I get that. Okay, so I'm going to use this thing to figure out my energy. All right, and I'm given the frequency, the wavelength in nanometers. So I'm going to convert this to meters again. So 671 nanometers, and I'm going to remember, I'm going to try to cancel the nanometers. So I have 10 to the 9th nanometers is 1 meter. So if I do that, I get that this is 6.71 times 10 to the minus 7th meters. Okay, and now this is my wavelength again. I'm going to throw that back in here. Okay, I want everything in SI units, so I can actually use the equation. E is equal to H. H is 6.626 times 10 to the minus 34th joules times second. H times C, which is the speed of light. Okay. and all this divided by the wavelength I just calculated. 6.71, sorry, 6.71 times 10 to the minus 7th meters. Meters cancel, seconds cancel, and I get joules, which is what I want. You throw that all in, and the energy from lithium is going to be tiny, but something that's still perceptible and detectable, and that's going to be 2.96 times 10 to the minus 19th joules. And as a matter of fact, lots of stuff, most stuff, is going to be within this realm of 10 to the minus 19th joules. I am not going to discuss this in this class. I just want to, an FYI basically, that we call this, these scientists often use, instead of joules, this thing called the electron volt, which has embedded in it basically the charge of the charge of an electron. And so you basically get rid of this 10 to the minus 19th on a factor too. So you're gonna have energies in numbers, in like numbers that are much easier to handle, rather than these tiny little things. So you're gonna drop this, and you're gonna have like 5 or 6 or 7 or something like that. It's much easier to handle than these fractions. Okay, so that's how you find the energy of a light, or the energy of an emission from an atom. Given either the frequency or the what do you call it, or the wavelength. All right, let's talk about Beer-Lambert's law. Okay, that's a little bit of a deviation from what we're doing, but it's an interesting thing nonetheless. It's related to this. It's just how do we use this to do actual important stuff. All right, so all matter can absorb light, and as it absorbs this light, it will gain internal energy. All right. So it will, if I have matter, I can calculate how much it will absorb, how much light it will absorb, and how it will use that absorption to give its particles, or whatever is embedded in it, the energy to do stuff with it. Okay, I can calculate that. I have machines. We have machines that are called spectroscopy. Basically, spectroscopic machines measure this absorption value. How much of an absorption of light is being seen by an object. Okay, so matter can absorb light, and we can measure it. That's what I'm trying to tell you. We can measure how much absorption a matter can absorb. Okay, and we can use this to our advantage. And basically, if I shine light on a bunch of solutions, I can measure how much is being absorbed. So if a solution has more stuff in it, it will absorb more light. And the equation that governs Beer-Lambert law is equal to A is equal to ABC. A is how much is being absorbed, that absorption I told you that we can measure. A and B, don't worry too much about them, but basically A is a material-specific constant. So sodium has an A, water has an A, I don't know, eggshells have an A. Everything has a little A for it, and you can either look it up or not worry about it, because I'll show you what happens. You don't have to actually calculate that. B is the path length. So if I'm shining light on a cup, right? If I have the bulb or whatever, and the detector on the other side, the length between the light bulb and the detector of the light, that's the path length. Okay, so that's usually kept constant. And then C is concentration. So all this nonsense seems so arcane. Let me show you what you actually could do with this. Here's a bunch of solutions that are of the same red stuff, whatever that is. I don't know, some salt that's red, whatever. Let's say I made a bunch of solutions that look like this. So the very dilute stuff, okay, line number 2 is gonna have this pinkish hue. And as I add more and more of this stuff to the solution, it will become redder and redder and redder. Okay, so what I'm going to do is I'm going to take my solutions here, and I'm going to put them into those machines I told you about that you will see in lab that can detect absorption of light. Okay, so the machine you're going to put this in the machine. Maybe the light source would be here, and the detector will be here, something like that. So it's got some sort of a length that it goes across, okay? And it's going to measure how much light got absorbed as it traveled from here to here. So obviously I have nothing here, it will be 0. I have more stuff, it'll start growing. And as I have more and more, it will grow. These are concentrations that I already know. I made 0.05 molar. I made 0.1 molar. I made 0.15 molar and 0.2 molar. I made this. So I know this. So basically what I'm saying is I'm going to translate what this concentration means in absorption values. Okay? And I know from this here equation here that A, the big A, which is this, and C, this C, are linearly correlated. So I'm going to plot A versus C. A is my Y value, C is my X value, okay? I am not going to worry about little a and little b. The hell with them. I don't need them. I need a big A and little c. That's going to give me everything I need, and I'll show you how. So I'm going to plot these values exactly like this. I put this in Excel. I put this as my Y, the red is my Y, and the black is my X. And when I did that, I got this. Okay, I have a same things that I just showed you a second ago. These numbers, I put them in Excel. I have A versus C, okay? And as it should, this thing should be a linear fit. And so I made a linear fit. It should have no y-intercept. A versus C is plus 0. So I have no y-intercept. Great. So I got this. Big A is equal to 4.805 C. What does it mean then? Okay, so what this means to me now is that I can calculate the concentration of any of this red stuff, okay? So let's say someone gives me a solution that's got an unknown concentration, and I want to know what concentration it is, okay? I'm going to put that in to my nifty machine that measures absorption values. It's going to spit out an absorption value. Maybe it's going to spit out, I don't know, 0.6 or something, right? So it spits out 0.6. I'm going to plug in 0.6 for A and solve for C. So then I can find C. Or I can use this chart. So 0.6 would be here, so it would be around 0.125 or something like that. Okay, so that's the power of Beer's law, or Beer-Lambert's law, that I can calculate the concentration of whatever I want if I make this calibration curve, and that's what I meant. I don't need to know little a and little b. They didn't come up. They're there. I kept them constant. I didn't change anything. If I changed my solute to something green or something, this thing would change. If I moved my detector away, this value would change. So you don't move it. Don't move it, and don't change the solute. Keep the same solute, and then you'll be fine. You're only changing A and C. This should be constant. Doesn't matter. Okay? And so you can construct this curve for anything you want, and that's what you're going to do in lab. Okay? So that's a little bit of introduction to that realm. All right.